Hi everybody, I hope you're doing well. In the present lecture, we will discuss a very important definition in quantum mechanics and in particular for the study of solid state, which is the density of states. The density of states will appear in problems related to the Fermi gas, the boson gas, which we will discuss in the next lectures, okay? So a density of states refers to the number of states allowed in a certain region of energies, okay, around E, some particular value of the energy, right? You define an interval of energies around a given energy value E. And if you divide the number of allowed states in that region, in that neighborhood, by delta E, in the limit where delta E goes to zero, you have a density, which is the number of states by energy interval. It is measured in states or number of states over electron volts or over joules if you are using the international system of units. Okay, so this is measured in states by electron volts, number of allowed states by electron volts. Okay, of course, you can also divide the total number of states by the volume of your sample. So you have the units as number of states per electron volt per cubic meter in the international system, or per cubic centimeter, or whatever the units of volume you are using in a particular case. Okay, so this is a very important definition, and we will try to calculate the density of states for a few particular and important situations. All right. Well, first, suppose you have a discrete energy scenario. Okay, so first situation, first case, discrete spectrum. Okay, if you have a discrete spectrum of our allowed states, your energy set, which corresponds to the solutions of this problem here, always we are referring to the eigenvalues of the time-independent Schrödinger equation. Okay, so the Hamiltonian has a discrete spectrum in this case. It could be atomic orbitals or atomic levels, for instance. So, as an example of these atomic orbitals, you'll have a set of energies labeled by quantum numbers in 3 dimensions, N, L, M, sigma. Or another example, infinite or finite, it can be a potential well. Okay, so if you are considering the bounded states or bound states here, you'll remember that in the case of an infinite potential well, the energy states will be labeled by an integer number n, and you have a energy scale defined as E sub 0 here times n squared, and n takes on the integers. 1, 2, 3, 4. Remember this E naught here, the energy scale, is just given by h bar squared, pi squared, divided by 2 times the mass of the particle times the size of your quantum well. Okay, so these are just a few examples of a discrete spectrum. Okay, and in this case, you'll have some energy E1, E2, E3. It is countable. You can eventually order in the ascending order of energies. Okay, it could be an infinite set or it could be a finite set according to the case. For the case of atomic orbitals in 3 dimensions, you will have an infinite set. In the case of rigid, perfectly rigid walls in a potential well, the potential barrier goes to infinity. At the borders of your box, you'll have an infinite set as well as in the case of an atomic orbital problem. But if you have a finite potential well, the number of bounded states will be finite and you have a discrete, still discrete, but finite set. Okay, so for this discrete spectrum, you need that the energy levels can be countable, okay, can be numerated by integers or or some discrete set of numbers, okay. And then you have in the energy line, you have exactly known values for the energies. Okay, so here you have some E n level, a superior limit of energies in the line. Only exact values are possible. So here you have a degeneracy. Suppose you have a degeneracy number. I will call it n1, n2, n sub n. Okay, so this is the degeneracy of the level. And in this particular case, if you divide the delta n, suppose around this arbitrary level n, over delta E, you will have exactly n with a subindex n over delta E in the limit of delta E going to 0 around this value here, and you have n states in an infinitesimal, okay, and this goes to infinity. So in this case, for a particular situation here, you'll have n states times the Dirac delta around that particular level. Okay, levels are discrete. There are very specific lines where the energy or points in the energy spectrum where there are allowed states. So you need to get closer and closer. If you pick a given delta E here around this energy, you get closer and closer to the specific value here. If you go for another interval of energies here, you can define a delta E, and there are no allowed states. So in this region, you have 0 states, but in particular values of the energy, you have a number. Okay, so you describe this scenario in a discrete spectrum, by Dirac deltas in the particular allowed levels. Okay, so the general situation for the density of states in this case will be a summation over n, okay, over n, the number of allowed states in a particular energy, which is a solution of the Hamiltonian here. I could insert an index here, delta, Dirac delta, okay, calculated as E minus En. And you sum over all the possible states from 1 to n, and this n, the capital N here, can go to infinity. So this is the density of states in a discrete scenario. Okay. So for quantum dots, as a very good approximation, you can just neglect the exact density of states. Suppose you have a spectrum here around a given state, but if this line here is well defined, or if you can consider that around some given energy, the width of the line is very narrow, you can describe it by a summation over Dirac deltas. Okay, just remember the definition, and if you want to calculate, the total number of states around the delta n around some given energy En, you can just use an integral over the density of states in an energy interval going from En minus delta E over 2 to En plus delta E over 2, and you integrate over the energies. Okay? And in this case, you will have 0 for this Dirac delta. It is 0 except at the point where the energy is exactly En. In this case, you have a degeneracy factor here. So you'll have a degeneracy number, which is the number of states allowed around the energy E sub index N. Okay, so this is what you have. If you want to calculate all the allowed states, all the possible states allowed, you need to integrate from minus infinity to infinity. Perhaps you have negative energies of the density of states, and you will find out a summation over 1 to a capital N, a total N here. Let me use another letter here. So a final, another symbol here, a final number of states. It could be infinite, perhaps, in the case of a discrete spectrum, but with an infinite possible solutions for the Hamiltonian, and you have this summation over all the possible states of your system. Right? Just remember that the Dirac delta, when you integrate the Dirac delta from minus infinity to infinity in a variable, a given variable, in this case it's energy, it produces 1. Okay? So if you have a degeneracy number multiplying this delta, you'll find out after integrating the degeneracy number. And if you integrate a summation of deltas, of Dirac deltas, you have a summation of the degeneracy factors here, a summation of these degeneracy factors. All right. So this is what you really expect in this case. Well, when you try to represent the Dirac delta to include, for instance, a so if you plot this density of states with respect to the energies, you'll find out in the allowed states E1, E2, E3, and so on, deltas. Okay, narrow lines, very narrow lines, which is zero for energies which do not coincide with a given possible allowed state in the spectrum, zero and infinite at the exact matches of the energy you are measuring with an allowed value in the spectrum. Okay, and the amplitudes of these deltas, it goes to infinity, but if you integrate, you need to find out the degeneracy of each level. So we could represent this delta as multiplied by some degeneracy factor, and 1 and 2 and 3 and so on. Okay, so when you integrate around this delta here, you'll find out the degeneracy of the energy level 1, the degeneracy of the energy level 2, and so on and so forth. This degeneracy could represent, for instance, if your energy is not discriminated by spin interactions of, or if it's degenerate with respect to spin, you could have the degeneracy of the levels, the number of allowed spin states. For fermions with 1/2 spin, it will be a factor of 2, okay, at each level. But in practice, if you allow interactions of your supposed quantum dot with thermal fluctuations, this would resemble not a perfect line here, but very narrow, but not exactly a Dirac delta. And therefore, you would replace a Dirac delta around a given state by something like a line width, which is called the gamma, the capital gamma, divided by something like E minus En squared plus this gamma n squared. And there is a normalization factor here, which is 1 over pi, I guess. So you replace the Dirac deltas by 1 over pi, gamma n, or the proper normalization factor, because if you integrate this around this energy En, you need to find out 1. This delta here is replaced by a representation using a Lorentzian. Or perhaps you can use another representation. Perhaps this is better represented by a Gaussian. Okay, but in practice, the Dirac deltas are replaced by some very tiny width here around the given possible energy, but is not exactly a delta, a Dirac delta. You have a width around an allowed energy state. Okay, so you have a more smoothly distributed possible allowed states, even in the ideal case where you have discrete levels. If you allow interactions with the thermal bath, you will find out very narrow states, but not exactly direct deltas. Okay, so this is for the case of discrete levels. You'll find out a set of nearly direct deltas or Lorentzian shaped peaks here or Gaussian around each possible states, allowed states. It is valid for the atom, okay? An atom has very, if you measure the possible lines corresponding to the atomic levels, you measure it using, for instance, optical measurements of a given atom, you will not find very exact lines at each atomic level, but perhaps narrow lines, not well defined direct deltas, but very tiny widths will be measured. Okay. Now let us focus on other very important problem, which is the second case, free particles. And I will consider here non-relativistic particles. In this case, you will have an energy spectrum. The solution for Schrödinger equation corresponds to something like that. E, depending on the wave vector, is h bar squared k squared over 2m, which is the mass of the particle. So k is the wave vector, and usually we do not write this vector, this arrow representing vector, because k squared is just scalar product of k with itself, and it produces the modulus squared for that vector, supposing, which is the case, the vector k is a real vector. In the case of quantum mechanics, it's a real vector. Remember, momentum is just Planck's constant times the wave vector, right? So this is general non-relativistic energy spectrum, okay? If you go make a plot with respect to k, the modulus of the wave vector, and we plot the energies as depending on k, you will find out a parabola, okay? So this is the spectrum we are considering here. You can do the math for a relativistic particle, so relativistic case, it has a spectrum of the form E squared over a given momentum, P, right, which is h bar k. This is the same for both cases, relativistic or non-relativistic. You have a quadratic spectrum, so a quadratic relation between the energy and momentum. So this is p squared times the velocity of light, usually, but it can be another velocity relevant for your problem. If you have a pseudo-relativistic relation, so the energy is squared is equal to c squared, some typical velocity of your system, p squared plus mass squared c to the 4. Okay. in the case, remember, in the case P going to zero, your energy will be the rest mass if you take the square root of this equation, so mc squared. Okay, but if you allow some kinetic term here, you have the energy. It has two solutions, a plus and a minus mc squared. A plus corresponds to the particle and the minus corresponds with a reinterpretation of this spectrum corresponds to the antiparticle. So electrons, mc squared, and the minus mc squared is reinterpreted as the positron with a positive mass, but with the reversed sign for the charge of the particle. So you have a energy corresponding to c squared p squared plus m squared c to the fourth, using all the units here of the international system. And if you just consider that the rest mass of your particle is very large compared to the kinetic energy, which is usually the case for non-relativistic situation, which is the approximation of non-relativistic mechanics, you can just write here in the following form: mc squared times the square root of 1, okay, because you plug in this, you factorize this m squared c to the fourth and find 1 plus the c squared p squared is divided by this factor here. You'll have a p squared divided by m squared c squared. Notice that now this normalization, this factorization here just produces a dimensional factor in the square root here. And if this unit, which comes from the m squared c to the fourth, is the dominant aspect, you can rewrite it as E approximately mc squared times 1 plus half p squared m squared c squared. And if you multiply it by mc squared, this is just a energy level which you can eliminate, because you measure energies with respect to this rest mass energy, this corresponding energy mc squared. You can measure energies from that level, mc squared, and what you can find is exactly this relation here. So the mass cancel one factor, c squared is eliminated, you have p squared divided by twice the mass, which is just this situation here with momentum replaced by the de Broglie relation. Okay, but this is for a massive particle. If you have a non-massive massless particle, okay, for a massless particle, mass is zero, and in this case you have a relativistic relation which corresponds to c times the modulus of the momentum, okay, and this is the case of a photon, okay, this is the case of a photon. Or in the case of a solid material or solid state, if you're trying to represent phonons, there are phonons which are very well represented by a relativistic relation of this type, massless particle, but the speed of light replaced by this sound, the speed of sound in that medium. Okay, so the relativistic case produces this case here in the limit of mc squared larger by one or two orders of magnitude at least than the kinetic term. So this factor dominates. You have mass, but the rest mass is very large. In the energy corresponding to rest mass is very large with respect to the kinetic term, or you have a massless particle, and in this case, you need to use a relativistic relation between energy and momentum. Okay, but here let us focus on the case of free non-relativistic particles. I can measure energies with respect to the mc squared. So I eliminate, I can write the energies, the energy E prime of P is equal to EP minus mc squared. Okay, this is what we are doing, and we arrive at this problem here. Okay, so what we want to do right now, we want to calculate the density of states. What is the density of states in this case here? What is the density of states in this case? So we have to consider the number of dimensions, space dimensions. So let us consider first one dimension, okay? One dimension of space. There is only one dimension. We have energy of K. I will let you calculate for two dimensions, because I will perform here the calculations for one dimension and three dimensions. The one-dimensional situation is very well to understand what you need to do. So the energy is a non-relativistic energy density. You can consider a line, and in this line over k here, which is just k of x, you can set a number of allowed values of k. All right, and if you just limit from 0 to some L in the line, okay, real line here, from 0 to some L in the real space, you'll have a set of solutions which corresponds to the lower bound on the delta k x, which corresponds to 2 pi over L. Okay, if you have a boundary condition for 0 and L in the line, which is very general boundary conditions, you know that the possible the minimum k will be 2 pi over L, and in the end you can let this L go to infinity, and you are at first dealing with the discrete spectrum for k, and between some a given k1 to a given k2 there is a distance 2 pi over L, right? This is the delta k which we are just considering here. Just remember that a given k of an integer number will be 2 pi over L times n, and in this case we are allowing in the end this L going to infinity. So the slightest of the possible values of k is 0, and then you have a 2 pi over L, which is infinitesimal, so it's a delta kx times a given integer number 1 and 2, 3, 4, and so on and so forth. In the limit where L goes to infinity, which is the length or the size of your system of the line in this case, in the limit where L go to infinity, the delta kx go to 0. So in the end, we can take the limit. L go to infinity. But now consider the following. What is the density of states? Density of states around a given energy corresponds to the number of allowed possible states divided by delta E. Okay? So I can write the delta E in the following form. I can use this equation, which corresponds to the dispersion relation between energy and momentum. And this produces h bar over m. I can calculate the derivative here. H bar over m, k, delta k. Right? So this is valid even in an arbitrary number of dimensions because it's the derivative of this relation here. And in this case, we will have delta n divided by h bar squared over m, a given k times delta k. Right? So around the energy E, I need to calculate, which depends on the given k. Okay, so we need to calculate the number of allowed states and divide it by h bar over m k delta k, because this is the delta E for an infinitesimal delta k. But the minimum delta k is 2 pi over L. And in this case, we have the density of states would correspond to 1 over delta k, which is L over 2 pi. Okay, this is the delta k here. The inverse is L over 2 pi. And we need to calculate delta n divided by delta k. I can now count the number of allowed states around the energy E with the given k, provided some delta k around that value, right? And in the end, I need to divide it by 1 over k because it's already here, okay? 1 over k, h bar squared divided by the mass. But from this equation here, I know that k is twice the mass divided by h bar squared times the energy, and we need to take the square root of the value, right? So this is what we need to perform, okay? And what is the number of states between some given k? Okay, let me erase here. Need to erase, but remember we are dealing with a one-dimensional problem. At first, what is the number of allowed values of energy states? What is the number around E of k? So what we can do, we just calculate the possible we can calculate the possible number of states in the line of kx between kx and kx plus delta kx. What is the number of possible states in this line here? So the number of possible states just corresponds to kx plus delta kx minus kx. Okay, I will have all the possible values, all the possible number of states in this line, which corresponds just to delta kx, right? Corresponds to that. And In this way, what we have a possible, this is the segment of the line, okay, this is the length of that line. So the possible states, if you are considering an infinitesimal delta k in the discrete case, the possible states between the kx plus delta k and the kx, the previous one, it is just one state, right? And therefore, what we have here is one state divided by h bar squared over m, and times k, and notice that well, this delta k we already have written as L over 2 pi here. Yes, delta n over delta e, delta n, h bar squared over m, k, delta k, all right? We have 1 here over h bar squared divided by mass times k, and this k here we already can calculate from the energy. In this case, density of states corresponds to the following: 1 over h bar over mass. I can insert the factor of 2 here, but to insert this factor here, this is just unit. I need to insert another factor of 2 here. So now I can rewrite this 2 over m h bar squared times the energy to the 1/2. And in this case, what we'll have is that this factor here is 1 over 2, okay, 1 over 2, h bar squared over 2m. I can rewrite it as 2m over h bar squared, but is divided by the same factor to the 1/2. Will produce twice the mass divided by h bar squared over 1/2, and we will have 1 over the square root of the energy. I cannot forget this factor here, the L over 2 pi, and therefore we have L over 2 pi here. And if you are taking into consideration the spin degeneracy, you are not correcting the energy by spin. You can count two possible spins. So if you are not separating the energies by spin, you'll have d of p is equal to, now we can insert here the degeneracy of spin, so it's times the ms for spin, and for spin half, this ns is equal to a factor of 2, which cancel this 2 here, and you have 2 over 2 times m over h bar squared, the square root of that factor, L over 2 pi, and 1 over the square root of the energy. So this is for one dimension. This is the density of states. If you plot here the density of states as a function of E, we will have for zero energy an infinite value, but it decays as a square root of the energy. Okay, so this decays. It is characteristic of a one-dimensional problem. This is the situation for one-dimensional density of states. We can see that from the solutions of the, the infinite square well, where the energies, if you consider a discrete spectrum, is some E0, which corresponds to the energy scale of your square well, infinite square well, and you can replace the A there by L, which will produce a infinitesimal E. But notice that for higher n, which is an integer here, the states become more and more separated, and therefore in an interval of delta E, which you can now relax the condition of delta E going to zero in the limit, you'll find out that the allowed states are more and more separated, and therefore for higher energy levels in this box, you have less and less allowed states, okay, because the energies in the case of a square well goes like n squared, right? In this case, you have for a one-dimensional problem this situation here, but just for one dimension, okay? Now we will calculate the three-dimensional situation. In three dimensions, we have the density of states. If we can insert spin, if you want to insert spin, we have a factor of 2, so I will use the subindex sigma for a given sigma, or up or down, just the total density of states. In the case of degenerate by spin, is a summation of over spin, the sigma of E. Okay, so this is a factor of 2 if the energies are the same for both spins. Okay, so what we have to calculate the same way, delta n divided by delta of energy. Okay, so the delta of energy still corresponds to h bar squared over 2m k over m, sorry, k delta k, right? But the delta n, which we want to calculate, now we have in three dimensions to really specify what this number is. Okay, we need to calculate the possible allowed states for a given value of around the given value of k. The energies are indexed by k. Okay, so we are trying to replace the density of state, the energies, by its representation over k, and then we come back to energy. Remember, k is square root of 2 times the mass, h bar squared, dividing factor here, times the energy. All right, so remember that factor, that fact. So what is the number of states for a given k? And let me draw a picture here in three dimensions in the k space, kx, ky, and kz. Okay, if you have a sphere in this space, you can draw another sphere here. So there is a sphere of radius k, and there is another sphere of radius k plus dk, an infinitesimal dk. There are two spheres. I don't know if you can see it properly, but what we have in the given interval, remember that the energy is just depending on k, all right? So in a given interval between k and k plus delta k, in this interval, we have a total number of allowed energies corresponds to the volume of the sphere in the k space given k plus dk or delta k minus the volume of the sphere k, right? So it is a difference of volumes because for a given value of modulus of k, right, in the k space, what is relevant is the modulus of k because it doesn't matter the direction of k, the energies are independent of that direction. Remember, the energies given a vector k, it just depends on the modulus of k. So you have a sphere for a constant modulus of k, you have a sphere of constant energy. So we need to calculate the delta n, the number of allowed states in this delta E interval. And the delta E interval corresponds to a delta K. Okay, so between K and K plus delta K, we have an interval of energies delta E. And we need to calculate the number of possible states here between these two spheres. In the limit, we take delta k, this dk here, going to 0. Okay, in the limit, we take that. But between these two values of k and k plus delta k, we have a volume. And in this volume, if I consider a small cube inside this, I can assume that around the cube I have just one point in the k space, in the space of the wave vectors, and the separation from another k point, it must correspond to the smallest distance between the various allowed k vectors, right? And just remember that this produces for a small cube, I have a delta k cubed. In the k space, this is the volume of this cube, delta k cubed. But remember, for a real space, if I take a sample of a material with lengths L for X, Y, and Z, the smallest delta k, which I can use, is 2 pi over L. It is the same as for the case of one dimension, okay, or two dimensions, because it corresponds to the smallest allowed value of k provided the if you provide the boundary conditions and you solve the quantum mechanical equations, the wave numbers, it's just the analogous of solving a problem of a string in one dimension or a membrane, a two-dimensional surface vibrating in two dimensions. And in three dimensions, you have waves with boundary conditions in the x, y, and z axis. But if you have a cubic volume in real space, you have a small cube here in the K space, and the smallest K value corresponds to 2 pi over L. This is the same as one dimension, but now you have three dimensions. And therefore, you have a delta n, which corresponds to a volume of a sphere, 4 pi over 3, k plus dk cubed minus 4 pi over 3 k cubed, and you divide this by 2 pi cubed over L cubed. But L cubed, remember, is the volume in real space. Okay, so this is the volume in the real space. And to make this calculation, you can use for this here k plus dk cubed. You can expand this by the binomial theorem or binomial relation, but you have a k cubed plus 3 times k squared dk, and the other terms goes in higher orders of dk squared and dk cubed, but this is to be taken in the limit of delta k going to 0. So we just stop here. And this k cubed here cancel this factor here, this 3 cancel this 1 over 3 here, and we will have the following relation. Okay, we will have delta n is equal to 4 pi k squared dk, which is to be considered an infinitesimal, and is divided by this factor here, which when we invert the order, L cubed divided by 2 pi to the cube. All right. And now we can insert it into the equation. All right. We can just insert it into the equation. And we will have a density of states for a given spin. If you consider degeneracy of spin, you multiply it by 2 for spin half particles, or whatever the degeneracy of spins is. Okay, so you have 4 pi k squared dk L cubed, which is the real volume, the volume in the real space, okay, divided by a factor of 2 pi cubed, and the delta of energy corresponds to h bar squared divided by the mass k dk. Notice that one factor of dk can be cancelled out, and in this case we have a factor of k, of course, also can be eliminated here, and we have the following. In 3 dimensions, we have d for a given spin as a function of the energy is equal to 4 pi divided by 2 pi cubed. We can just calculate what is left in the end. But now we can plug in a factor of 2 here and a factor of 2 here. So this h bar over m I can rewrite as twice the mass divided by h bar squared. And this factor of 2 cancel one factor here. So I'll have a factor of 2. Okay. And now we can insert the value of k, which is just twice the mass divided by h bar squared times the energy, and there is the volume of the sample cube. All right. Now we can simplify the constants, and we will have one factor of 2 pi is cancelled out. You have a 1 over 4 pi squared. If you have spin degeneracy here, you multiply for fermions a factor of 2 here. So this is 2 pi squared. Okay. And you have twice the mass of the particle over h bar squared to the 3 halves. Okay. Because now you have 2m over h bar squared, twice the mass, just the 3 halves, square root of the energy. Okay, this is what is produced in 3 dimensions. So the density of states for a given spin as a function of the energy goes like the square root of the energy. Okay, for parabolic dispersion, you have a square root of the energy, and it increases as the square root of the energy for higher energies. Okay, so this is the density of states in the three-dimensional case. 3D. You can show, I will left it as an exercise. You can show that the density of states is proportional. You have to find out what is the proportionality constant, but the density of states for parabolic relation is proportional to the number of dimensions minus 1 divided by 3, by 2, sorry, divided by 2. Okay, sorry, minus 2. Yeah. So it is proportional to the energy to d minus 2 over 2. Okay, in 3 dimensions you have a 1 half, in 1 dimension you have a minus 1 half, and in 2 dimensions you can show that the density of states is a constant because 2 dimensions cancel this factor of 2. So this d here is the number of spatial dimensions. Okay. So if you are neglecting any corrections of energy due to spin, you can insert the degeneracy factor for fermions, which is 2 for spin half fermion, and it will be 1 over 2 pi squared, this factor here, okay, this 2m over h bar squared to the 3 halves square root of the energy. In any case, when you are calculating something, for instance, if you want to calculate the total number of particles, what you need to do is n, the total number of particles, corresponds to an integral over density of states times the probability function, which is Bose-Einstein or Fermi-Dirac, according to what is the type of particle. So this is the probability function from perhaps minus infinity to infinity, if the density of states has any value for negative energies. For instance, in this case, it has not any possible values, so the density of states is 0 for negative energies, because it's nonsensical to talk about a complex number for density of states. So it's 0 and starts from the energy equals to 0 here. Okay, and therefore in this particular case it starts from 0, but it is limited by the density of states. And this is the Fermi-Dirac distribution for fermions, or a Bose-Einstein distribution for boson particles, and you need to integrate over dE. If you want to calculate the average of the energy of your system, you need to integrate from minus infinity to infinity the operator here, which you are trying to measure, the density of states with that energy, times the probability of occupation times, or integrated over the energies of your system. Okay, so if you want to calculate the energy here, energy of your system, the number of particles, or whatever quantities you want to calculate, it depends on the density of states. The density of states quite naturally appears when you replace a discrete summation over k by, suppose, in 3 dimensions, an integral over d3k. You will have a volume here divided by 2 pi cubed. And when you have a spherical symmetry here, you just need to remember that d3k can be replaced by 4 pi k dk, and this k dk for a parabolic relation. If you remember, ek is equal to h bar over 2m k squared. The differential over energy corresponds to h bar squared over m k dk. Therefore, you can replace, sorry, it's k squared here, and the 4 pi is corresponding to the integrals over theta and phi, the angles. Okay, so if you already integrated the angles, you have a 4 pi for the sphere, and this k squared dk you need to replace here by an integral over the energies. If you do that, you'll find out the density of states. Of course, you have spins, summation over spins continue, but the d3k you can replace by an integral over dk, and this integral over dk you can rewrite it as 4 pi k squared d integrated over d energy. You rewrite this k squared as a function of energy, and you can insert here dE over dk. So the density of states can be related to volume over 2 pi cubed. Okay, so in the case of replacing a summation by an integral, you can consider that the density of states is a volume over 2 pi cubed, a 4 pi, which comes from converting this integral in spherical coordinates, if your system is spherically symmetric, 4 pi, a k squared over, or as a function of the energy divided by the differential of the energy over the differential of k. And this is just in the case h bar squared over m k. In 3 dimensions, this is what you have. And you can just, in the end, replace everything by a function of energy. Okay, in 2 dimensions, if you have 2 dimensions, you can convert this 2k as d2k is volume in 2 dimensional spaces and area as 2 pi k dk, and notice that when you divide by this factor k dk, it cancels out, and the density of states is a constant in 2 dimensions. And in 1 dimension you can do the same, but the integral is just a replacement over L over 2 pi integrated over dk. And okay, just calculate in 2 dimensions, but in the end, the density of states will appear in calculations for the total number of particles, the energy of your system, and magnetization of your system or whatever physical quantity you want to calculate, it will be related to the density of states. And of course, energy by thermodynamic relations, if you want to consider thermodynamics, you want to calculate, for instance, specific heat. Okay, so specific heat of a system at constant volume. You calculate something like this. The C with constant volume is related to minus 1 over V, the time derivative of the energy with respect to temperature. And if you can, you I guess is a minus sign here, but let me write it as proportional to the energy derivative, the total energy of your system with respect to temperature. Okay, this is the specific heat at a constant volume. You can calculate pressure. Of course, you can calculate pressure, which corresponds to the derivative of the mean energy with respect to volume, in this case, at constant temperature. Here it's constant volume, constant temperature, and so on. You can calculate pressure, and you need to, in the end, you need to calculate the averages of the energies of your system. Okay, so we will use the definitions of density of states, and it's a very, very important aspect in the theory of solids or the quantum theory of solids. It allows you to calculate many properties of your system. You can measure the density of states or infer from some measurements. Okay, and well, I'm finishing here this topic on the density of states, which is a preparation for a discussion of the Fermi gas and the Bose gas or bosonic gas or the black body radiation in the case of photons, or for calculations of a specific heat contribution coming from phonons in the solid. But I'll see you next time. Bye.